Malheur Bassin, Eastern Oregon, late October 1837. While his fellow trappers pitched canvas wedge tents in 20 minutes, 41-year-old Elias Hart was still gathering willow poles and weaving cattail mats, building a dome shelter he'd learned from northern Paiute families. His neighbors called it wasteful. Pike barked that weed basket would blow apart in the first norther. Crowder sneered it was a beehive fit for bees. Then January 9th arrived. 3 days of brutal northeast wind drove temperatures to 10 below zero on the basin flats. Canvas tents glazed white with rime. Frost fell in sheets inside the wedges. Men burned armloads of willow just to survive, feeding stoves every hour through the night. But Hart's stupid reed basket maintained 28 degrees with zero fire. 38 degrees warmer than the frozen air outside. No frost, no dripping, just steady warmth from woven grass. What did this Ohio trapper understand about staying warm that 2 centuries of proven canvas wisdom had completely missed? Hart had arrived at the willow rise above the spring on October 27th after watching the last geese lift off the marshes around Malheur Lake. At 41, the Ohio-born trapper carried skills most mountain men lacked: greenwood bending from wagon work back in his home state, and cordage techniques picked up repairing pack saddles across 2 decades of wilderness travel. But his most valuable knowledge came from 2 winters spent living among northern Paiute families in this very country, learning their method for surviving the brutal Great Basin cold. The Paiute winter house was elegant in its simplicity. A willow-framed dome 8 to 15 feet across, blanketed with woven cattail and tule mats overlapped like shingles around a central smoke hole. Hart had watched Wadatika band builders select straight willow shoots, set rings of binder poles at 18-inch intervals, and lash the mats in overlapping courses that shed weather like a thatched roof. These structures clustered near springs every winter, used year after year, staying tight and dry when canvas glazed with rime. The trapping camp neighbors, Ephraim Pike, Silas Crowder, and Tom Beaulieu, represented frontier orthodoxy. They'd spent seasons on the open flats dealing with the region's notorious dry northeast winds and sudden temperature drops. Their method was speed and simplicity: pitch a canvas wedge or wall tent, bank it with snow, and feed a fire through the cold snaps. Pike favored the wedge tent because it went up in 20 minutes with just a pole ridge and guy lines. Crowder trusted his wall tent with its small sheet iron stove. Beaulieu threw a lean-to against whatever windbreak he could find. When they saw Hart's willow bundles and reed gathering, their derision came swift and cutting. Beyond the initial mockery, Beaulieu snorted about wasting 3 days weaving grass when 20 minutes pitched a proper canvas shelter. Pike questioned the sanity of building a permanent structure when the trapping season demanded mobility. The criticism reflected deep-seated assumptions about frontier survival. Speed trumped comfort, proven methods beat experiments, and canvas represented civilization's advance over primitive shelters. Hart understood their skepticism, but held firm to what he'd observed. Canvas tents suffered from a fundamental flaw in cold weather. Single-skin fabrics trapped, exhaled moisture, and frosted unless heavily vented, creating a cycle of dampness and heat loss that forced constant fire tending. He'd spent miserable nights in wedge tents watching frost accumulate on interior walls, feeling the clammy canvas drip as temperatures fluctuated around freezing. The Paiute method solved this through breathability and insulation. Cattail and tool stems were naturally hollow, trapping air like modern insulation. When woven into mats and layered in multiple courses, they created a wall that breathed, moving small amounts of moisture outward instead of condensing inside. The overlapped shingle pattern shed rain and snow while allowing vapor transmission, exactly what modern building science calls vapor-open construction. Hart planned modifications beyond standard Paiute practice. Where typical mats measured 2 to 3 inches thick, he aimed for 3 to 4 inches, knowing the extra thickness would boost thermal performance. He calculated 4 to 6 full courses around the dome, more wraps than usual, to create a truly integrated weather shell. The foundation would get a heavy skirt of loose tule to stop splash and drafts at ground level. His choice of location followed indigenous wisdom. The Paiute always built near springs for winter camps, understanding that these sites offered reliable water, protection from prevailing winds, and the marsh resources needed for construction and repair. Hart's chosen rise provided drainage while keeping him close to the cattail beds he'd need for materials. The technical aspects reflected skills learned through careful observation. He'd watched Paiute builders cut stems low for maximum length, bundle them 8 to 10 inches thick, and rack dry them in shade until they turned from green to pale straw color. Rushing this step, using green, undried materials, led to shrinkage problems and loose lashings after the first hard frost. Proper preparation meant methodical cutting, bundling, drying, then twining mats to consistent dimensions before transport. As October faded toward November, the philosophical divide in camp became clear. Hart represented adaptation, a willingness to learn from indigenous knowledge and apply it to frontier survival. His critics embodied the conventional wisdom that had carried men across the continent: stick with proven methods, prioritize speed over comfort, and trust in the tools of civilization. Neither side suspected that the coming winter would test these competing philosophies with life and death precision. Hart began construction on the first day of November, eager to complete his shelter before the serious cold arrived. His impatience led to the critical error that nearly doomed the entire project. Instead of following the methodical Paiute process he'd observed, he rushed to the marsh edge and pulled fresh cattail and tool stems directly from the standing water. The green stalks felt substantial in his hands, thick, sturdy, and seemingly perfect for immediate use. Working through the afternoon, he twisted several mats from these undried reeds, his fingers moving quickly through the familiar twining motion he'd learned from northern Paiute women. The fresh mats appeared sound as he lashed them to the willow frame. The green stems held their shape well, the twining felt tight, and the initial courses went on smoothly. Hart stepped back that evening satisfied with his progress, watching the dome take shape against the darkening sky. The structure looked solid, the mat courses properly overlapped, and the lashings secure through the binder rings. The first hard frost struck 3 nights later, dropping temperatures to 20 degrees below freezing. Hart woke to discover his fundamental mistake. The green cattail stems had shrunk dramatically as cellular moisture froze and sublimated away. Where the stalks had measured nearly an inch across when fresh, they now contracted to half their diameter. The twining rows that had been tight the previous evening now showed gaps where the shrunken stems pulled away from each other. Worse, the rawhide lashings that had secured each mat to the binder rings hung loose and slack. Morning light revealed the full extent of the problem. The mat edges cupped inward where moisture loss had caused uneven shrinkage. Several sections showed finger-width gaps along the twining rows, creating potential points for wind and snow infiltration. The carefully overlapped shingle pattern had shifted as individual mats contracted, leaving vulnerable seams exposed to weather. Hart ran his hand along the shell, feeling the give in lashings that had been drum-tight days before. His Paiute teachers had warned explicitly about this failure mode. Green reeds contained too much water to provide stable construction material. The traditional method demanded patience. Cut stems low near the root for maximum length and strength, bundle them loosely to 8 or 10 inches thick, then rack them off the ground in shade where air could circulate freely. The drying process continued until the stems turned from bright green to pale straw color, indicating moisture content had dropped to equilibrium with ambient humidity. Hart spent the next 2 days implementing the correct sequence. He returned to the marsh with his knife, selecting only the straightest stems and cutting them low near the waterline. Each bundle went onto elevated racks he constructed from spare willow poles, positioned to catch breeze but avoid direct sun that might cause checking or splitting. He turned the bundles daily, monitoring the color change that indicated proper curing. While the new materials dried, he addressed the dome's structural issues. The original frame needed reinforcement with a proper binder rhythm. He added outer binders at 24, 42, and 60 inches high, creating anchor points where each course of matting could be tied through to interior support rings. This system distributed loads more evenly and prevented the sagging that had begun to appear in the original lashings. The foundation required attention as well. Hart gathered loose tulle and cattail stems, packing them into a thick skirt around the dome's base. This backstop would shed splash from rain or melting snow while blocking drafts that might penetrate at ground level. The packed foundation extended 18 inches from the shell in all directions, creating a thermal break between the interior and the cold earth. As the properly dried materials became ready, Hart began rematting the entire structure. He standardized each mat to 24 inches wide and approximately 3 inches thick, with lengths calculated to carry completely around the shell's circumference. 5 full courses would circle the dome, each overlapping the one below in true shingle fashion. The weave needed to sing under hand pressure, tight enough to shed weather, but not so compressed as to eliminate the air spaces that provided insulation. Interior details demanded equal precision. Hart deepened the hearth hollow directly under the smoke hole, creating a fire pit that would draw properly and contain coals safely. The doorway faced slightly east to dodge the prevailing northwest winds that swept across the basin during winter storms. A doubled mat served as the door covering, designed to overlap the opening completely while remaining easy to move for entry and exit. After 3 days of methodical retwining and relashing, the corrected dome stood transformed. The shell felt solid under pressure, the weave tight and uniform. No light leaked through the mat courses, and the door covering lay snug against its frame without gaps. Hart had learned the hard lesson that separated successful frontier adaptation from dangerous improvisation. Traditional techniques evolved through generations of testing, and shortcuts usually led to failure when survival depended on getting every detail right. As Hart worked through his reconstruction, the trapping camp began to fracture along predictable lines. Luther Ames, a methodical trapper who'd survived enough brutal winters to respect unconventional solutions, started asking practical questions. How thick should the mats be? What kind of knots held best in freezing weather? Did the smoke hole size matter for draft control? His inquiries carried the tone of a man evaluating rather than dismissing, someone who'd learned that survival often came from unexpected sources. Malachi Quinn, typically quiet around camp, also began lingering near Hart's work site. Quinn had spent enough nights in glazed canvas to understand the misery of waking to frost-covered bedrolls and dripping tent walls. He watched Hart's technique with the focused attention of someone calculating whether the extra labor might pay dividends when temperatures dropped. His questions centered on materials, where to find the straightest willows, how to judge when reeds were properly dried, whether different marsh plants might work equally well. Meanwhile, Ephraim Pike and Silas Crowder hardened their opposition. Pike's mockery grew more pointed as the dome neared completion, calling it a fool's waste of time when proven methods worked fine. He pointed to his own wedge tent, pitched and ready in the time Hart spent just gathering materials. Crowder echoed the sentiment, emphasizing that wall tents had carried trappers through countless winters without requiring specialized knowledge of reed weaving or indigenous techniques. The arrival of Mary Wilkins shifted the camp dynamic unexpectedly. The freighter's wife had stopped with the supply train moving across the basin, her husband Daniel leading a string of pack animals loaded with goods for trading posts farther west. Mary possessed the practical eye of someone who'd spent seasons evaluating shelters along freight routes, comparing their performance against the demands of weather and logistics. When Hart invited her to examine the interior of his completed dome, she stepped inside and immediately noted the difference. The space smelled sweet and warm, she observed, lacking the clammy mustiness that plagued canvas shelters in cold weather. The woven walls felt dry to her touch, without the condensation that typically beaded on tent fabric during temperature swings. Most tellingly, the interior maintained a comfortable temperature despite the lack of active heating, something she'd never experienced in conventional canvas structures. Jonas Keenan represented the camp's pragmatic middle ground. An experienced hand who'd built countless windbreaks and lean-tos across the territories, he appreciated Hart's craftsmanship while remaining skeptical of wholesale abandonment of proven methods. His offer to help came with conditions. He'd assist with construction if Hart would consider throwing a canvas wall tent over the completed reed structure, combining indigenous technique with frontier practicality. The suggestion revealed his thinking: take the best of both approaches rather than betting everything on untested methods. Hart's explanations carried the authority of direct observation rather than theoretical speculation. Cattail and tool stems were naturally hollow, he pointed out, trapping dead airspace like the down in waterfowl feathers. When woven into overlapping mats, these air pockets created insulation that canvas simply couldn't match. More importantly, the reed construction breathed vapor could migrate outward through the mat walls instead of condensing on interior surfaces. This vapor permeability prevented the ice buildup that made canvas tents so miserable during freeze-thaw cycles. The physics were straightforward once explained. Single-skin canvas created a sealed environment where exhaled moisture had nowhere to go except onto the coldest surface, typically the tent walls facing outside air. In freezing conditions, this moisture formed frost that melted during warmer periods, creating cycles of dampness and chill. The reed mat shell allowed moisture to migrate gradually through the wall thickness, maintaining interior dryness without sacrificing weather protection. Hart completed his dome with careful attention to indigenous specifications. The interior diameter measured 12 feet, providing adequate floor space for a single occupant plus gear storage. The crown peaked at 8.5 feet, tall enough for comfortable movement while maintaining structural strength. 24 willow rafters, each 12 to 14 feet long, formed the frame with inner binder rings spaced at 18-inch intervals for secure mat attachment. The floor received equal consideration. Hart spread layers of sagebrush and willow withes to create a springy, insulating barrier between sleeping areas and the cold ground. The natural materials provided cushioning while allowing air circulation that prevented moisture accumulation beneath bedding. His cache boxes and personal gear found secure positions around the dome's perimeter, protected from weather while remaining easily accessible. In contrast, his neighbors completed their shelters with characteristic frontier efficiency. Pike's wedge tent went up in 20 minutes, requiring only a ridgepole and guy line staked to the frozen ground. Crowder erected his wall tent with practiced speed, positioning his small sheet iron stove for optimal heating while maintaining safe clearances from canvas walls. Keenan constructed his tarp-roofed lean-to against a convenient cottonwood snag, creating wind protection with minimal materials and labor. By November's end, the small basin community had crystallized into distinct camps. 2 men remained curious about Hart's methods. 2 continued their vocal skepticism, and the completed structures stood as physical embodiments of competing survival philosophies. The straw-colored dome on its willow knoll represented centuries of refined indigenous engineering, while the canvas shelters around it embodied frontier pragmatism and speed. Winter would soon test which approach better served human survival in the Great Basin's unforgiving climate. The killing cold arrived on January 9, 1838, in the form of a dry northeast wind that scoured the basin flats and drove night temperatures to 10 degrees below zero. This was the test Hart had anticipated, not just bitter cold, but the specific combination of wind, low humidity, and radiative cooling that challenged every heating system in the high desert. The clear skies that accompanied the Arctic air mass meant no insulating cloud cover, allowing ground heat to radiate freely into space and creating the kind of deep, penetrating cold that could kill unprepared travelers. By dawn on the 10th, the canvas shelters revealed their fundamental limitations. Pike's wedge tent had transformed into a frost factory, its single-wall construction creating perfect conditions for moisture condensation. Every breath Pike exhaled condensed instantly on the interior canvas, where it froze into a coating of hoarfrost that grew thicker through the night. When he shifted position or the wind shook the tent, sheets of ice crystals fell onto his bedding and gear. Despite burning armloads of willow branches, he couldn't break the cycle. Heat from the fire drove moisture from his breath and body, which immediately condensed on the coldest surface available. Crowder's wall tent, with its sheet iron stove, performed marginally better, but still failed to solve the moisture problem. The interior walls wept steadily as warm, humid air from his breathing met the cold canvas. Even with the stove burning hot, ice formed along the tent's perimeter by morning, creating a crust that had to be scraped away and dried before it could melt and soak his belongings. The cycle repeated nightly: heat, condensation, freezing, melting, drying, forcing him to tend the fire every 45 to 60 minutes just to maintain marginal habitability. Keenan's tarpon bough lean-to suffered additional problems as spindrift worked under the eaves during wind gusts. The arrangement provided wind protection but little thermal benefit, and his bedroll grew clammy with absorbed moisture that had nowhere to escape. Without the enclosed space that canvas provided, he faced direct exposure to air movement that stripped body heat faster than his small fire could replace it. Inside Hart's reed mat dome, thermodynamics worked according to different principles entirely. With no active heating beyond his own body warmth, the interior stabilized at 28 degrees, a 38-degree improvement over the brutal ambient conditions outside. The hollow cattail stems that comprised the mat walls trapped dead air in millions of tiny cells, creating an insulation barrier that slowed heat transfer while allowing vapor transmission. Unlike the sealed environment of canvas tents, moisture from Hart's breathing could migrate gradually through the reed walls instead of condensing on interior surfaces. When Hart lit a small cooking fire using 3 or 4 wrist-thick willow sticks, the interior temperature quickly climbed to 55 degrees and held steady. The central hearth design, copied directly from Paiute winter houses, created a natural chimney effect that drew smoke cleanly through the crown opening without creating downdrafts or interior air circulation that would strip body heat. More importantly, the vapor-permeable walls prevented the buildup of humid air that plagued enclosed canvas structures. The structural performance differences became equally apparent as the wind continued through the second day. Pike's wedge tent snapped and strained against its guy lines, transmitting every gust through the fabric into the interior space. The canvas acted like a drumhead, amplifying wind noise and creating vibrations that prevented restful sleep. Crowder's wall tent performed better structurally, but still required constant adjustment of stakes and guy lines to maintain proper tension as the fabric stretched and contracted with temperature changes. Hart's dome responded to wind loading like the engineered structure it represented. The overlapped mat courses and heavy foundation skirt shed gusts without flapping or noise transmission. The multiple wrapping layers, 4 to 6 courses around the circumference, distributed loads evenly across the willow frame, while the shingle pattern prevented wind from catching individual mat edges. The structure's aerodynamic shape deflected airflow rather than creating the flat surfaces that made canvas shelters vulnerable to wind loading. Fuel consumption revealed the most dramatic performance difference. While Crowder burned wood continuously to maintain marginal comfort, Hart used perhaps 1/10 as much fuel, a few sticks at dusk for cooking, a handful more before sleep for warmth. The superior insulation and vapor management of the reed mat construction retained heat efficiently instead of requiring constant energy input to offset losses through condensation cycles and thermal bridging. By the morning of January 11th, the comparison had resolved itself beyond argument. The canvas shelters had fought a losing battle against basic physics, creating conditions that were damp, cold, and fuel-intensive despite their occupants' best efforts. Hart's dome had maintained comfortable conditions using passive thermal design and minimal active heating, proving that indigenous engineering could outperform frontier conventional wisdom when properly applied. The men who had mocked the weed basket now faced an uncomfortable truth. Their proven methods had failed, while the despised alternative succeeded completely. Pike emerged from his frost-covered wedge tent looking haggard and cold. Crowder appeared equally worn down by nights of constant fire tending. Meanwhile, Hart stepped from his warm, dry shelter, rested and ready for the day ahead, having slept comfortably through the worst cold the Great Basin could deliver. The conversion began within hours of the cold snap's end. Pike, who had spent 3 nights scraping frost from his tent walls and burning through his wood supply, approached Hart with grudging curiosity. The man who had called the dome a weed basket now wanted to understand why his proven methods had failed so completely. Crowder followed shortly after, his usual bluster replaced by practical questions about reed selection and mat construction. Both men had reached the same uncomfortable conclusion: Their canvas shelters had nearly killed them, while Hart's despised basket had provided comfort they'd never experienced in winter camping. Hart's instruction proved as methodical as his construction technique. He walked the converts through reed identification first, teaching them to distinguish between different marsh plants and select specimens with the proper characteristics. Cattail provided the best insulation due to its naturally segmented stem structure, while tulle offered superior weather resistance when properly woven. Both required cutting at specific times, after the growing season ended but before winter damage weakened the stems. The drying process demanded patience that frontier pragmatism typically rejected. Hart demonstrated proper bundling techniques, showing how loose arrangements allowed air circulation while preventing the mold and rot that could ruin entire harvests. He emphasized color changes as indicators. Green stems contained too much moisture, while properly cured material turned pale straw color throughout. Rushing this stage led to the shrinkage problems that had nearly doomed his own first attempt. Mat construction required skills most trappers lacked but could learn through practice. Hart taught the basic twining technique, showing how to maintain consistent thickness while creating the tight weave necessary for weather protection. Each mat needed to measure approximately 24 inches wide and 3 inches thick, with lengths calculated to the specific dome circumference. Too thin and the insulation failed. Too thick and the mats became unwieldy and difficult to lash properly. The frame construction followed Paiute engineering principles refined through centuries of use. Hart demonstrated proper willow selection, emphasizing straight grain and appropriate diameter for structural loads. The binder ring system required precise spacing. 18-inch intervals provided optimal support without creating excessive weight or complexity. Each ring needed secure lashing to the vertical rafters, creating anchor points where mat courses could be tied through for maximum stability. Within 6 months, the technique had spread beyond the immediate camp. Luther Ames successfully completed his own reed mat dome before the following winter, reporting similar performance during a February cold snap that dropped temperatures to 15 below zero. Malachi Quinn taught the method to his brother's trapping crew, who built 3 domes along the Silvies River drainage. Daniel Wilkins carried the knowledge back to his freight operations, where drivers began constructing reed shelters at regular stopping points along their routes. By 1840, word had reached wintering parties across the Great Basin's river corridors. A crew working the Humboldt River drainage reported building 5 reed mat domes during an exceptionally harsh winter, with all structures outperforming canvas alternatives in fuel efficiency and interior comfort. Trappers operating near Goose Lake adopted the method for seasonal camps, standardizing mat dimensions and construction sequences to speed assembly while maintaining performance. The geographic spread reflected the method's practical advantages over conventional alternatives. Unlike canvas shelters that required constant maintenance and fuel consumption, reed mat domes provided superior thermal performance with minimal ongoing input. The vapor-permeable construction eliminated condensation problems that plagued single-wall tents, while the natural insulation properties of hollow plant stems created thermal barriers that canvas could never match. Those who adopted Hart's technique universally praised its comfort and efficiency. The reed mat dome became known among Great Basin trappers as the most effective portable winter shelter available, warmer than canvas, more durable than lean-tos, and capable of renovation and repair using locally available materials. Veterans reported that a properly constructed dome could be disassembled, transported, and re-erected at new locations, making it practical for semi-permanent camps and seasonal operations. Modern building science would eventually validate what Hart learned through observation and necessity. Research conducted more than a century later confirmed that cattail and other marsh plants possess thermal conductivity values comparable to commercial insulation materials. Laboratory testing of cattail-based panels yielded thermal conductivity measurements between 0.04 and 0.055 watts per meter Kelvin, performance levels that matched mineral wool and approached extruded polystyrene foam. Contemporary hygrothermal analysis explained the vapor management principles that made reed mat construction superior to sealed canvas. The naturally porous structure allowed moisture vapor to migrate through wall assemblies instead of condensing on interior surfaces, preventing the freeze-thaw cycles that created miserable conditions in conventional tents. This breathability, combined with capillary action within the plant fibers, actively transported moisture away from occupied spaces. The story of Hart's reed mat dome entered Great Basin folklore as proof that frontier survival often demanded learning from indigenous knowledge rather than relying solely on imported techniques. The method became part of winter routines across marsh country, handed down through trapping crews and freight operations as a quiet testament to the power of traditional engineering over fashionable equipment.